Good evening. Welcome to the QCIS channel. We're on this channel. You get a daily dose of science, technology, engineering, and math. And tonight, I'm going to talk about something that is related to fluid mechanics. And what it is, we're going to deal with open channel flow. Now, there are different types of channels that we utilize open channel flow, and you also have to find the what we call the wetted perimeter. Now, what is the wetted perimeter? Well, that is the perimeter of a particular shape of a channel that is wet. Like you would have a trapezoidal, that's one of the popular ones. You could also have a V, you have a circular, and you basically in fluid mechanics, you can plug that into a head loss type of problem where you take a certain number, like if you're dealing with SI units, it's 1,000 over N times A times R to the 2/3, S to the 1/3, somewhere like that. But when we deal with open channel, well, what is open channel? We're talking about the flow. Open channel flow refers to the movement of a liquid, typically water, in a channel where the fluid surface is exposed to the atmosphere, meaning it has a free surface and it is not completely enclosed like a pipe. Examples include rivers, canals, streams, where the flow is driven primarily by gravity and it can be observed directly at the water surface. Now, key points you need to know about open channel flow: it's a free surface, and it's the defining characteristic of open channel flow. It's the presence of a visible free surface exposed to the air. It's also gravity driven, and the flow is primarily driven by the force of gravity. Also, the applications where you have open channel flow, it's studied in various fields like civil engineering, water resource management, environmental engineering to analyze and design systems like irrigation canals, river channels, and of course, storm drains. So when we deal with open channel flow, we have a couple of equations. Now, the basic relationships, we have an energy equation, resistance equations, momentum equations, and continuity equations. Now, it's very important, particularly if you're studying, I would say mainly civil engineering. Now, of course, you will see some of this in mechanical engineering, but basically with mechanical engineering, you're going to see a lot of pumps. Now, this does come from fluid mechanics. Now, again, when we deal with flow, of course, we're going to have introductions, going to be effective discharge, shear stress, pattern and profile, open channel hydraulics, resistance equations, compound channel, sediment transport, bed load movement, land use, and of course, land use change. All right, when we deal with the continuity equation, we're basically taking inflow, subtracting outflow, and then we get a change in storage. Now, where would you find something like that? You would basically look at a reservoir. That's where you would find that. Now, the general flow equation, and if you're in fluid mechanics, you're going to always see this. You're going to see Q equals V times A. Now, your Q is your flow rate. Now, for the most part, here in America, we use English or Old English units. So we're going to use CFS, which is cubic feet per second. Now, the SI units, it's cubic meters per second. And then you have your average velocity of flow at a cross section, feet per second or meters per second. You can have the area of the cross section, feet squared or meters squared. Now, you know everything is okay when your units match up. If your units don't match up, something is wrong. Okay, your resistance equation. You have Manning's equation. You have the Darcy-Weisbach equation. And of course, velocity distribution in a channel. So basically, depth average velocity is above the bed at about 0.4 times the depth. And here's the map. You have your channel bottom right here. You have your relative velocity, and this is your water surface. And of course, this is your depth, and this is your distance from the center line. Here's your center line. So you're going to go either 6 feet to the right or 6 feet to the left. And again, this symbol right here is your soil or your channel bottom. Now, one of my favorite equations, if you want to find velocity, you must use the Manning equation. Now, Manning, he was an Irish engineer, and he came up with this equation. V, that's your velocity, equals 1.49. They rounded up to 1.49, but I already know it's 1.486 divided by N, R to the 2/3, S to the 1/3. Now, so you'll understand what the variables are. V is the flow velocity in feet per second. N is known as Manning's N, and it is a coefficient of roughness. R is the hydraulic radius, where you have A divided by P. P is your wetted perimeter. S is the channel slope bed as a fraction. And of course, 1.49 is a unit conversion factor. Again, you use 1 if the SI metric units are being used. Now you have your reference, your roughness coefficients, type of channel, and description. So you have your streams. You have your streams on plane. You have your clean, straight, full stage, no rips or deep pools. And this is what your chart would look like. In fact, you would actually, if you were utilizing Manning's equation to find a velocity, you would use these numbers. These are your roughness coefficients. You might not be able to see this. Let me blow it up a little bit so you can see it. Okay. Right here, let me go back down a little bit. You have your channel conditions. Here's your N, your N1, your N2, your depth of irregularity, your various cross sections. This is all of your soil. Now, you will find this a lot if you're doing water resources engineering, environmental engineering as well. This is why you have to know fluid mechanics if you're going into civil engineering. You'll have this little chart right here. So I show you all the way at the bottom. And then we see it right up here. It's a little bit better right here. What you have here are your values for the computation of the roughness coefficient. That's what you saw on the previous page. This one's in much better legibility here. That's what it is. All right. You also have an example problem, velocity and discharge. So channel geometry known, depth of flow known, determinant velocity and the discharge. Now, first of all, we have a rectangle here. So when I do an area of a rectangle, say 20 by 1.5 feet, it's going to give us about 30 feet squared, 30 square feet. And if you really want to plug in values, this is where you're going to utilize Manning's equation. You're already given your slope. So that's going to be your S. You're already given your N. That's Manning's equation. That's your coefficient, your roughness coefficient. So when you go in, you plug everything in, This is what you get. Now, your perimeter. This is your perimeter right here. So basically, you have a rectangle. Now, you notice in a rectangle, it's generally 2 times the length plus 2 times the width. But you notice you don't see it here. Why? Because you're basically dealing with your wetted perimeter. That is the area that is wet. So you do not utilize the whole rectangle. Now, some people might call it B plus 2y. I like to make it simple. If you're dealing with perimeter, you just add the sides. So basically, that's what they did here. They got your R, they got your S, you plug everything in, and that is Manning's equation. But you got to find Q as well. You remember, Q is your cubic feet per second. That's what they found here. They found Q. Now, if I wanted to find the velocity, well, what am I going to do? I'm going to manipulate the formula. I'm just going to take Q divided by A. And they give you another one. You already have your Q. Q is your discharge, your flow, bed slope, stream on a plane. So what are you going to do? Well, go to this chart right here, and you're going to utilize your coefficients, your roughness coefficients. That's what you're going to utilize here. And utilizing your roughness coefficient, let me move this over here. Let me trim it down. Actually, let me go back up, go back to my screen. There we go. Here's me right here. All right, there you go right there. There is the situation right there. That's much better. You can see all of your information. These are all your roughness coefficients. This is good if you're going to be taking the FE examination. That is what you're going to use with all this information. All right, let's go down a little further. Right. Let's exit full screen mode here. Let's move this over here. There's your other coefficients. Let's go down again. This is bear with me here. Let me stop share. Let me get right back in it. Let me get right back in it. There we go. Let me just this over here a little bit. All right, we got your solution. This is what you get here. This is your Q right here. Again, you're utilizing your area. Areas width times depth. And this is a good equation because, again, if you're in fluid mechanics or if you're designing any type of channel, you're going to have to use these equations. Again, here's another version of the equation. What is G? Generally, G is your gravity, 9.8 to 32.2 meters per second or feet per second. That's what that is. All right, just bear with me here. Let me cut that out. Let me go right back in. Right. And of course, there's another version. And I'm learning myself. A lot of versions of this equation, but you need to know it. There's another version. Again, flow in compound channels. And as you look at it, most flow occurs in main channel. However, during flood events, overbank flows may occur. In this case, the channel is broken into cross-sectional parts and the sum of the flow is calculated in various parts. Now you're going to have flow in compound channels. Natural channels often have a main channel and an overbank section. Your overbank section, and here's your main channel. Again, we're going to use Manning's equation. Now, what is this N and the sigma I equals 1? Well, in determining R, only that part of the wet perimeter in contact with an actual channel boundary is used. Generally, that we're utilizing the summation. And again, this is your wetted perimeter over here. And let's move it here. We have our sub areas. Area of discharge. You have your other variations here. Manning's in. Probably get into Manning's equation a little bit now. And what I'm going to do, I'm going to go into Excel, and I'm going to do a little bit of Manning's equations. I like to do it with Excel. I also like to do it by hand as well. I'm just giving you an overview on what it looks like, but I will actually do some problems. Again, here's a section plan. And this is if you were designing it. Okay, and there's your flow, your overbank flow. Excuse me for the technology here. Picture might have been a little big, might have hit something. But again, just giving you a lesson here on what it looks like. Overbank flows, and here's your deep overbank flow. And basically that's really it for your uniform open channel flow. Now I like open channel flow. Now there are other equations if you're going to have rainfall events. If you're going to be designing any type of new drainage, stormwater, and use a lot of those equations. No, I call it open channel flow. It's really called open channel hydraulics. Very good to get into, especially if you are working for a DOT and you really want some year-round work. This is the best work to get into. Why? Unless the ground is really freezing, you'll be able to work all year round. You can't do paving all year round, but you can lay pipe all year round. And there are a lot of areas that are laying new pipe structures. Now remember, when you actually do this kind of work as well, you have to have some velocity. some slope. Now, you don't want it too steep because you'll have a fast velocity. When you have a fast velocity, there's a chance that you're going to have a clog at the other end. But you don't want to have it too slow either because you're going to have buildup as well. You want to have it enough so it drains. And again, I'm going to get into various types of channels. And I'm looking forward to doing some of the problems for you. And I'm going to use that one problem. Now, basically, too, as I said before, when you do problems like this, you have to watch your units. If you are in English units, you're going to use cubic feet per second, CFS, or I usually write it FT3 over S. Using length over time. Remember that. And you know it works because your other variables, they're going to be part of it. Because you may have to take, let's say if you're doing a pipe, you might be taking a diameter. And generally a diameter is pi d squared over 4 if it's a circular diameter. And that's going to be in square feet. And then you're going to have a velocity, which is in feet per second. Now, once you do all the work, it's going to be correct. And it's going to be the same way if you find it the other way around. Now, there's going to be head loss problems, continuity equations where you're going to have to do Z's and V's and cancel everything out. Your Bernoulli equations. We're going to have to set one equal to another. It's where it can get sticky. It's almost like you're doing statics. Basically like you're doing statics. We'll get into some statics later on too. But just wanted to give you an overview on the open channel flow. Of course, if you like what I just presented, please comment, share, and subscribe. And if you're looking for some more political and social content, you can check my other channel out every Wednesday. I go on to the 411 Talk Zone radio show. And once I record all of my videos from the 411 Talk Zone radio show, I post the videos up to YouTube, Twitter, formerly X, Rumble, and Truth Social. And for this channel, the QCIS channel, generally every Thursday I do a video. If I'm a little tired, I might wait till Saturday to do the video, but generally you're going to have a STEM video following my political and social videos. And you're also going to find me on YouTube, because once I finish this video, I'm going to upload it to Twitter or X. And I'm also uploaded to LinkedIn. And for everybody on LinkedIn, let me tell you this. I know I get individuals that want to connect. If you want to talk to me about STEM, I don't have a problem connecting with you. If you're from these other companies I don't know about, investment companies, this is a STEM channel. I'm not interested in selling my business. I'm not interested in accounting. If you want that, go find other channels that do that. This is a STEM channel. So if you want to reach out to me with some STEM, certainly we can connect. Because I've been getting a number of individuals who are sending me emails and they want to connect. Well, I'm not here to connect with anybody unless you are part of the STEM field. That is the whole purpose of my channel. That's why some of you, when I go on my LinkedIn, you're not getting any responses from me because I've said it many times, and when you don't listen, I'm not one that's going to block you. I'm just going to ignore you. So if you have some STEM topics and you want to go live, just let me know. You can hit me up at lej6521@gmail.com or lej6521@yahoo.com. Let me know if you have a STEM topic. We'll get on StreamYards and we'll talk about it. Or we can hit each other up in the comment section. But other than that, that concludes this content on Open Channel Flow right here, QCIS channel. On this channel, get a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.